So for this freestyle on 3.5, I'm not going to do too much calculus. I just want to kind of remind you of how to do an inverse real quick, okay? So say, for example, that I have the function y equals 2x. The way to find the inverse is to flip x and y. And so I get x equals 2y, and you're like, okay, but what do I do with that? Well, we're not used to looking at things in terms of x. We're not used to having x be the thing that has been solved for. So what do you want to do? You probably want to divide by 2 here and divide by 2 here, and then you'll end up with y equals 1/2 x. And so these two functions are inverses of each other. The fact that we flipped x and y can be very confusing. So a lot of times what we'll do is we'll say this function is really, let's call it f of x, right, with our function notation. And so when I find the inverse of f of x, I want to have a way of telling you that this specifically is the inverse of the original function. And we do that with this terrible notation right here with that -1 being up there in the exponent. Please don't ever say that exponent out loud. The way that you say this whole big mess out loud, what you say, the words that you use are the inverse of f, okay? So please do not say some crazy power. I'm not looking for that. I didn't make this notation up, and I'm not very fond of it. So that's why I get upset when you say it like it was a power. It's not a power. It's just a way of saying that we found the inverse, and the inverse, oh, by the way, this is 2x. This should be 1/2 x. Okay? Now, imagine that I used any other number. For example, I could use a 3 here, and then I would get a 1/3 there. I could use a 4 here, and I would get a 1/4 there, and so on and so forth. I wanted to show you real quick. I did do 1/3 and 3 as being my slopes. I just kind of wanted to show you that the cool thing about inverses is that they are mirrors of one another. And they're mirrors across that green line. The green line you could see is y equals x, and that's why we flip x and y, is because we make y be equal to x, and we make x be equal to y. And so anytime I graph a function and its inverse, it will always look like a mirror image, like the mirror was that green line. And so we have our original function. If our original function was, say, 3x, that's the red line, and then therefore my inverse would be my inverse would be the blue line, which is 1/3x. And I accidentally said that word negative, and I regret it, because it's very important that you know that there's no negativing. You know, there's nothing, I'm not taking opposites, I'm taking inverses. So it's interesting, right? You're like, that's not quite the same. In fact, if you wanted to try one that was just like slightly harder, finding an inverse that would be a little bit more difficult, we could try something like this. Y equals, 2/5 x, and why not? I'll throw a minus sign in there just for the heck of it. And how do I go about finding the inverse of that? Well, first step, I'm going to take x and I'm going to move it over here, and I'm going to have 2/5, and I'm going to say y, and then I'm going to have that -6. And now what do? I want to solve this for y. And so there is an operation here where I add 6 to both sides. And by the way, I'm going to put this 2/5 over here because my goal was to solve for y, and a lot of people like it when y is on the left. So I'm just moving that over there. And then I have all of this, x plus 6, and I'm going to move it on this side of the equal sign now, x plus 6. And then when I want to solve for y, shouldn't I multiply by the reciprocal, 5/2? Oh yeah, I remember this, right? I'm hoping that you do. And so now I say then that these guys turn into 1, because, right, 5 times 2 is 10, and 2 times 5 is 10, and 10/10 is equal to 1. So I've solved for y, and I can also not forget to distribute to everything, because I wasn't just trying to get rid of it on one side. I want to use a property of equality, so I'm going to do it on every little piece. So now I have 5/2 x, and then I have this unpleasant mess where I have to figure out, well, 5/2 times 6 is, and let's say that I get 30/2, which ends up being 15. Aha, there is a plus 15 here now. And so when we started out, if I called this f of x, you might not have been able to guess right, what the inverse would look like. Here's what the inverse looks like. 5 halves x plus 15. Okay, maybe you couldn't have, but I will point this out. You notice that and that? Huh. Those are reciprocals of one another. In fact, up here, when I was talking about it before, 2 and 1/2, those are both also reciprocals of one another. And so leading you into the next lecture section, I wanted to point out to you that when I talk about the slope of a linear function, remember that that slope is constant. We're going to find out that when we want to find the derivative of an inverse function, we're going to be able to see that that slope should be a reciprocal. And I'm going to write it right now. So the inverse, no, sorry, the inverse is down here. The inverse function can have a derivative. So do you see me putting that awful, terrible -1 power up there? That's the notation that tells you that I have an inverse. And now I'm putting this prime mark on the outside. I threw the parentheses down. It's supposed to help your eyes track. You're supposed to be able to see now that I'm saying the derivative. Oops. Sorry about these artifacts. Sometimes I accidentally hit my keyboard. There. The derivative of the inverse. That's what that notation means. It should be a reciprocal. The reciprocal of the slope of the original function. So if I got a 2 as my original slope, well then I will get a 1/2 as my reciprocal inverse derivative slope. Whew, a lot of vocabulary there. Same thing down here, by the way. If I take f of x and I find its derivative, I end up with a 2/5. And when I take f's inverse, there's f's inverse, and I take the derivative of that, I would get, well, the derivative of 5/2 x is going to be 5/2, which is the reciprocal. Okay, so that's what I wanted to cover with you, except for one other little more thing. So in the lecture notes, you'll see that I'm talking about a quadratic, and its inverse would be a square root, and so you're going to see that. But we also have another question down here, which talks about a function that just looks a little bit more scary, a little bit more involved. And so let me talk about this function for just a moment. It is f of x equals x cubed minus 2x plus 7. And I am going to take the derivative of it at some point. But what if I was asked to find the inverse of this? Now, it might not have been a part of your course of instruction to talk about, well, when can't you find an inverse? Like, why can't I find an inverse? So here I'm going to say, let's rename f of x into y. And so I have x cubed minus 2x plus 7. And then I said all you had to do was flop those, right? So, okay, if I flop them, what do I get? I get x equals y cubed. Wait a minute. Look, there's another place where there's another x. Am I supposed to replace that x with a y as well? Yes, you are supposed to replace every x with a y. So this is a -2, and there's a y, and then a plus 7. And by the way, Desmos can graph this. It'll graph it with the x being, I'm going to say quote unquote in the wrong place. Desmos is a computer program, so it totally can graph it. And it's actually might be fun to do that. Graph this function. You can actually literally type that whole command in, and then you can graph this function and type that whole command in, and you'll be able to see, hey, those things really are inversible. But algebraically, we have difficulty with solving this for y. So can you solve for y? Question mark. Well, I mean, what would the first step be? The first step would be to minus 7 for both sides. Always trying to get rid of constants, right? And then again, I like to put my y's on the left, so I'm going to put them over here. So I'm going to have y cubed minus 2y, and then I have all of this, x minus 7, and I'm going to put it on the right. And so I have x minus 7, and it's looking better, right? But now I have two quantities over here, and they're separated by a minus sign, and those y values, like how many y's do I have? Right here I have 3 y's, right there I only have 1 y. So how can I gather this up so that I only have a single y, where a y equals something? I mean, yes, I could factor a y out, and I could say that y times y squared minus 2 is what I'm getting, but that didn't really help me get y by itself. I mean, I could divide even by y squared minus 2, but then I still have a y squared. I have this y squared. So that's, you know, I do have y equals something, but there's still a y in the wrong place. I need that y, this y squared, to be on the left somehow, and I really can't do that. So not possible to solve for y. And our handy trick of being able to think about, like, say for example, like what's the slope, or what's the constant, or what's the y-intercept. You know, we have little tricks in algebra that help us manipulate equations. Makes us feel like this isn't really an equation, is it? Is it really a function? But I say yes, it is. Absolutely, it is a function, and we can do stuff with it. For example, I could make an XY table and just start graphing some values. But I'll mention, I probably would pick my y's first. I'd probably pick, like, say I want y to be 0. Because if I say that y is 0, then I have 0 cubed minus 2 times 0 plus 7. And then x would have to equal 7, right? Because 0 cubed is 0, and negative 2 times 0 is 0, and 0 plus 7 is 7. So you see, I could still definitely pick some points, and I could still graph them. And so if you're interested in more of what this function looks like, it's a cubic, only it's been flipped on the y equals x axis. And go ahead and throw it into Desmos so you can see it. And once you visualize it, then you'll realize that yes, there are definitely slopes that can be gleaned. We can figure out how to find slopes. We just have to be more creative about it. Hence the reasoning behind the next section. How do you go about finding the value of the derivative of the inverse at that inversed point? Turns out the trick is going to be simple. It's going to be find the reciprocal. Once you flip the point, you should be able to find the reciprocal at that point. So go ahead and take a look at that video.